Welcome everyone on the first non-keynote session of the last day of Code BMV. I'm Stavros Aronis. I will be hosting the session and trying to manage time and questions and all of that. This is a fireside chat, but there's very little preparation that me and the speakers have made beforehand. So there's a lot of time to get your questions on the floor and go as deep as you would like to go. But we'll start with an introduction so that we get everybody on the same baseline about what the just-in-time compiler is and what all this amazing work is about. Would you like to introduce yourselves, Lukas and John?
Sure. My name is Lukas. I'm a consultant at Ericsson. I work normally for Erlang Solutions. I've been working on this just-in-time compiler together with some other colleagues at the Ericsson OTP team. One of them is John, Björn, and Don, and a lot of people were involved in this effort. I've been at the Ericsson OTP team for 10 years now, I think, 11 years. I lost count, so it's been a while, and I've been doing various things there for a long time.
John?
Yeah, my name's John. I've been working at the OTP team for the past 4 years, roughly. Mostly involved with the compiler and runtime system. And this past year, I've been working on the JIT quite a lot.
Great, thank you very much. Let's have a brief introduction on what the JIT is about. And I know that that Lukas wants to share some.
Yes, so I will do a brief introduction. I've talked about this at various conferences and podcasts and things before, so I'm going to be brief here. So one of the mottos, so just-in-time compiler basically means that we are compiling code just in time. So when we need it, we are compiling it into native code instead of previously, as we did, it was interpreted. So this gets rid of various overheads and so on, and there's a lot of different languages that use this, like Java is the most famous example, but also things like JavaScript and many others do similar things to varying degrees. The motto kind of that we had when we designed our flavor of JIT that we called BIMASM is keeping things simple. So we have tried various more complicated solutions in the past. And after a lot of trial and error, we settled on a very simple solution. The basic solution is that normally in the interpreter, what would happen is that we would parse the .beam files that you compile there, and that's kind of, so on this image here, we can see this is kind of the compiler working. So it parses the code, it optimizes it a bit, and it emits the beam files over here. And then in runtime, what we do is that we parse the opcodes, and then for the just-in-time compiler, we emit the native code there, and then we execute native code here. In the interpreter, instead, we would parse the opcodes. We would emit the opcodes into an intermediate format that would be interpreted at runtime. So there would be there's various trade-offs into why you want to make an interpreter and what you want to make a native compiler or a just-in-time compiler in that way. And mostly it has to do with maintenance burden. You need to spend a lot of more time maintaining something if you are doing a just-in-time compiler, because you need to have different backends for different platforms and so on and so forth. Let's see if I can click here. So our just-in-time compiler translates Beam code to native code very directly, does very few other optimizations. It does do a few, but not very many, and it's 100% compatible with the interpreter. So if you're running, you can still run the interpreter and it works the same way. In our current version, we translate to Intel x86, but we have been working for the last, 3-4 months together with the person responsible for the code emitter that we use. So that's the ASM JIT code emitter. We've been working on getting the ARM JIT, and kind of happy to announce that we have something that works very well. And I will stop for a minute, and my colleague here, John, will open the pull request on GitHub for the ARM backend, so that we now have an ARM backend working. Let's see if I can, maybe I should do this. I can go here. Okay, let's see if I can come to the right place.
We should have conferences more frequently so that we get more stuff from, and have you to talk to the conference, Lukas, more frequently.
I don't know. I'm not sure this will become a habit, but maybe eventually. So here we have PR open, so you can go out and try it on your fancy M1.
Wait, we don't see the screen though. I think I don't see the screen. Does anybody else do?
Did I share the wrong?
No, it was.
Yeah, now we're in presentation mode thing here. Let's see. Whatever. You can have a look at it yourself. It's not rocket science.
Nice, great.
So that we've done that. So now it works. So the ASM JIT has support for ARM, and now we in BMASM also have it. And it's mostly John and Bjorn, or solely John and Bjorn that have worked on this, not me. There I've been sitting sharing on the sidelines. There. So that's nice. And it makes a big difference on running on Macs. John, do you want to add something?
Not really. Just like the old JIT, it makes a big difference. Performance improvements ranging from 30-40% to twice as fast. It's just better.
Yeah, it's better. And part of the reason, as far as I gather, is that the interpreter is also worse on the M1s than on the Intels because of various reasons. So it has more to catch up on. You're very happy with the results. And I feel that it was easier to do the ARM than I expected it to be. What do you think, John?
Yeah, ARM is a much more cleaner architecture than x86. You don't have to keep as many things in mind while writing ARM code. So taking the scaffolding we had from x86 and porting it to ARM didn't take very long. I think it took us maybe 2.5 to 3 weeks to reach the prompt, and then another 2 weeks to have all tests passing. So it was very quick and convenient, surprisingly quick and convenient, actually. So
yeah,
we're very happy with how it turned out and the entire project.
Nice. And this kind of prompts a question: what is next? What other architectures are in plan, if any, or what is this? What's the roadmap there?
Well, we don't plan on adding any more architectures at the moment. This kind of project is, we did it somewhat quickly. It went quicker than expected, but it's still a lot of work, and it's work that we cannot spend on. We can't spend this time on anything else. And since we don't have anyone screaming at us, telling us to get RISC-V or ARM32 or any other architecture working, we don't have any concrete plans on adding them. We have quite a few plans on. We have quite a few ideas on how to improve our existing JITs, and we would much rather spend our time on that than trying to port the JIT to more architectures.
Which now prompts another question to the top. What are improvements that you want to explore? This is a question from Jose Valin. What improvements do you have in mind that you want to explore? What type of optimization? Is it type-driven optimizations? What is it? What is in the plan?
One of the optimizations we want to explore in 25 and maybe 26 is they are mostly type driven. It's like the Erlang compiler does quite a lot of type optimization on the Beam code, but it doesn't really pass this information into the Beam file. The JIT is completely unaware of the types that may go into an instruction. So let's say that the compiler knows that, yeah, we have A plus B here, and we know that both of these arguments, both the left-hand and right-hand side, are integers. The compiler may know that, but we don't pass that information into the Beam file, so the JIT has no clue and still has to handle the cases where the arguments are largely unknown and the user could have provided an atom. So we have to emit code to check the types. And that's actually quite a significant amount of code. Well, it's a very small amount of code per instruction, but taken in an entire release, it's a lot. So we plan on cutting that out in 25 or 26 by propagating type information. I think that's the biggest improvement we have in mind short term.
Yeah, and it's I suppose we could do that kind of work by emitting more specialized instructions in the compiler as well, but we kind of want to keep a good abstraction level in between the two, so that we do some things in the JIT and some things in the compiler. But we don't have any general plans to do more like profiling in runtime or that kinds of things for the just-in-time compiler, as there are quite a lot of hurdles in order to be able to switch between different kinds of code and doing optimizations of things and then de-optimizing those parts. And that's problems that are hard to solve, and it takes a lot of time to solve, I should say. Maybe not hard, but take a lot of time to solve. And we have unique problems in Erlang because we have so many processes running at the same time. Like if you're doing the same thing with what's they called on-stack replacement algorithms in Java, you have 100 threads, 1,000 threads max that you need to go. In Erlang, you have millions of processes that you need to do these kinds of things on, and it just doesn't scale to do that kind of solution. So you have to be creative. So we are not really planning on doing anything runtime profiling that would recompile the code or something like that.
So that's more of a optimization that you will not do rather than optimization you will do.
Not yet, anyway. Maybe somebody on doing a master thesis or something will slap into LLVM into our compile chain instead of doing AsmJIT and see what the LLVM compiler can do with the code emission instead of using AsmJIT and see if it can beat it. I don't know. Maybe it can. Maybe it can't.
But it's this kind of flow of information is it follows from the natural evolution of the other compilers. The Hype compiler had this type information that was driving some optimizations. Dialyzer got this information and made warnings. Now some of these have been back in the main compiler, and now they flow again down to the just-in-time compiler that you have. Yeah, it's a long history of this kind of thing moving up and down the abstraction chain, perhaps. Let's see. Going back to the Q&A as it's ranked. One of the big side effects of the just-in-time compiler has been the support from standard Linux tools, and for example, tools for doing profiling, such as perf and all the interesting things that you have written down in blogs. And the question that I had actually is, how will this affect the future of Erlang's own profiling tools, eProf, fprof? Are these things still relevant, or are these things going to be superseded completely by standard tool chains now?
It depends. They will still be relevant. Some of them will still be relevant because the standard tool chain can't profile per process, Erlang process, like the Linux chain. So you can't get a profile saying, I just want to do profiling on this specific gen server and see what it is doing. You can't ask the Linux operating system to do that, or any other for that matter. And we always say Linux here because Linux is really the only one that has the best support for it at the moment. There is some support that we've played with on OS X as well there, but it's very Linux centric, the tools, and not everybody runs Linux. Quite a few people run like FreeBSD and other things on their servers there. But I'm hoping that as we explore more and get more information, we will be able to use these tools more and more and more to get different insights and so on, and people playing around, because the number of tools that use perf is so much greater, and it's like it feels like every other week somebody sends me a link, but have you tried this way of visualizing things from perf, or this way of visualizing? And it's just more and more people and tools are using this there. But I don't think eProf, fprof, or cprof will go away because they have the Erlang perspective on the which process, Erlang process is it that spends the most time running? You can't answer that question using Linux tools. You can guess from the call frames, but you can't know.
Mm-hmm. And another related question by Peter Nyomori. Do you want to unmute yourself and ask directly? I can go ahead and place it. Linux also has standard tools for tracing, and of course we have had some tracing with systemtab on Erlang, but Peter's mentioning tools like DBPF based. How do these tools? Where do these tools now fit in, apart from profiling?
We don't have a lot of experience with DBPF yet there, so we haven't experimented with what you can do and what you can't do with those. It seems that it might complement some of them, and you can definitely do more complex analysis using eBPF to see what the program does and so on. And this using the JIT opens up, but I think it should theoretically be possible to do the kind of profiling that you would want to do if the kind of profiling that eBPF allows or introspections on should be possible to do even with the interpreter. It just is a bit more complex to run those kinds of things in there. You just need to find the correct symbols and so on inside of the emulator. But I have not, I don't have, and I don't think John has either played with eBPF. I've run it once or twice to see what it can do. And in theory, it should be able to do a lot of things, but I have not used it in practice.
Mm-hmm. Next question from Mikael Pettersson. Would you like to unmute and ask?
Yes, so this is a question about the linkage in the generated code. So are there any code size limitations on the generated code, or placement limitations, like for instance forcing all code to reside below the 4 GB boundary? And nope. Also, do you have any support structures like PLTs or GOTs to assist linkage?
We have no limitations on code size or linkage. We don't really link. We call different modules using export entries, just like before.
So this means that in general, you will always need to synthesize 64-bit values before making calls.
Between modules, yes, we load the code pointer from the export entry and we jump there, yes. But within the module, it's simple branches. if a branch is too far, we emit a small chunk of code that loads a full 64-bit pointer to the actual address and then jumps when necessary. So we've tried to hide all limitations. So you shouldn't ever notice them. Code might get a tiny bit slower if you have a module that ends up being larger than 128 megs. But in general, they shouldn't, because the generated code is actually a pinch smaller than interpreted code. So I hope that answers your question.
Yes, this is an area that often gets premature optimizations if you look at things like ELF and standard ABIs. So you seem to have gone from the other end, allow the wider pointer sizes from the start, so you don't run into these problems.
I think we had those problems early in development, but we've fixed them as we go along.
Yeah, really early on, we did not add these things because we didn't have a decent abstraction for it at that point. But we hit the problem almost immediately. Right when we hit the prompt, we had to load a Unicode module, and that Unicode module was big enough to cause problems. So we had to solve it the second week. So.
Okay, thank you.
A very, again, specific question from Sergei Prokhorov. Would you like to ask in person? Question is, the ASM JIT, which is the technology powering the just-in-time compiler, does not have ARM support in master. Do you use some fork of it? How does that work?
We're using a pre-release branch. You can find it on GitHub under the name ARC64. So the Erlang Ecosystem Foundation is sponsoring the development of that branch, and it should be merged to master quite soon. Mm-hmm. The PR I just opened has bundled the pre-release branch so people can try it out. But it's going to be stable very soon, as far as I know.
All right. So this is the Erlang Ecosystem Foundation pushing the other projects that Erlang is standing on then in some way, which is amazing, I think.
Yeah, and I must say the person, even before the Erlang Ecosystem Foundation got involved, the person maintaining ASMJIT has been incredibly responsive to all things, like any bug report or any fix that we've wanted to get into upstream. It's like one day afterwards he's responded, merged it, or proposed his own fix. So it's yeah, it really feels like it was the right bet on that, to use that project to do that, because he responds way too quickly for, yeah, I don't know, much more quickly than we do, certainly on our pull requests.
But this prompts me to intervene with a loaded question. So you said the person maintaining this. How is the ASMJIT maintained? Is this the larger project? Is this something that I know that, for example, the just-in-time compiler, the Erlang OTP now is vendoring ASMJIT because of that. But how do you see the maintenance of this moving forward? Is it something that now OTP owns sufficiently? Is it something that you will rely on to some external entity? And how stable is that relationship, as far as you can tell?
As far as I can tell, we have a good relationship. We will continue. We kind of also chose ASMJIT because there was a code base that was small enough and easy enough for us to do patches and understand ourselves, so that if the person decides that, no, this is not fun anymore, or I don't want to do this anymore, we can kind of pick up and fix things in our own vendored version, and possibly kind of merge patches and so on up. I don't think we will do any major development or things in that package. there, but we do bug fixes and so on, and the code is relatively simple to follow. So that's kind of our plan anyway. So if he stops supporting it, we will have to have our own patches and do those things, and that seems reasonable. It's a good base to build on.
Great. A question from Sergey Prokhorov again. How do you ensure that the just-in-time and interpreter don't have any discrepancies in code behavior? How is this now guaranteed?
We run our tests. Is the simple answer to that. Our test suites test the behavior of all of our instructions and everywhere. And if we have to make differences in our code in the test suites, then there's a difference in the way it works. We have had to make some changes when it comes to timing things, because all of a sudden things run faster and we had timing issues in test cases. But besides that, there have been really no major changes inside of any of the things. For instance, I believe there's a test suite that tests kind of the interactive shell that Björn, a colleague, has been spending a lot of time lately trying to develop, because all of a sudden the shell on the Mac was so responsive that all of the timers and everything just went haywire. So you had to write a mini expect language to solve that. So it's kind of, yeah, that's the kind of problems we've had. And all of the other parts, I mean, if you run the compiler suite and the emulator suite, you have good coverage of that things work the way they should, as far as we know.
Mm-hmm. It's usually the case that you see your tests behaving in unexpected ways when your environment is too slow, not when your environment is too fast. It's interesting to see this kind of thing showing up in.
It's the first time it's happened to us as well.
Nice. So what about a question from Pablo Lopez Viqueira?
Hi.
Yeah. Go ahead.
Okay, so the question is, do you think that could be useful to have some kind of tool that combines the output of perf and the output of already existing Erlang profiling tools like fprof or EP or eprof or any of them?
Good question. I don't know. Do you have any good intuition, John?
No, not really.
Spontaneously, I would say no, because it would be hard to combine that kind of the data. But I mean, when profiling, I would kind of use the Linux-based tools first to kind of get a general idea of what is happening in your system. And then if you need more information, to kind of drill down with the Erlang-based tools to get more details out of the system, because the Erlang-based tools are more detailed in what they provide there. And if it's possible to make some kind of automatic tool like that, that would be awesome. Like if you just run something in Erlang perf thing, and then it runs perf, and then it sees like, oh, these things are spending a lot of CPU times in these frames, and then it automatically enables fprof on the node and for only those frames to see which processes it is that it's running, and then it brings back the result or something. I don't know, something like that. That could be a nice integration between the two, possibly. I don't know. Yeah, but that, I don't know how well that will work. But
thank you very much.
What about, so another dimension there could be perhaps making Erlang tools that would make information shown in perf, for example, more interesting. Looping the code in such a way that adds enough things so that perf and standard tools can pick things then. But again, this is development of new tools, and the design space there is infinite.
Yes.
On the subject of types, John Klinger has a question.
Yes, I was wondering, you mentioned how you like save type information to be able to optimize the JIT more efficiently. Would like Gleam or Caramel or like new BM languages that are statically typed be able to leverage this like in a better way compared to say Erlang on Elixir?
Not really. All of those go through the Erlang compiler in the end, and it's the Erlang compiler's types that we'll end up using, because we can't actually trust anyone else's types. I mean, if they could maybe post-process the Beam files or something, but we're not going to be able to use them, at least not starting out.
Or for instance, I don't know, like if you add a guard or something in your code based on the function signature, that will help, or?
Yeah, they are adding guards will help the Erlang compiler figure out types. The Erlang compiler essentially has its own built-in version of dialyzer that uses success typing to figure out what's possible and what's not. Okay. So if you know that something going in must be an atom, then you can use a guard, is atom, and the compiler will simply assume that, yes, this variable is going to be an atom from here on out.
But you cannot, if you put a guard like that and then do an external call from another module, even if Gleam or Camel has proven that all calls will always be atoms going in there, that atom check, we still need to do that. Otherwise, yeah, scary things might happen.
Specialize. And
what about private functions in this case? Would you skip the guard checks?
Yes. Like dialyzer, everything goes when it's private local functions. We know what they will return. We know what's passed in. We know that they cannot be hot code upgraded to anything else. The big problem when calling an external module is that all of a sudden someone, even if you know that, yeah, this is only ever going to return a 2-tuple, between calling and it returning, you could have had a code upgrade that suddenly made it return a 3-tuple or an atom or simply crashing. And the compiler can't know. The compiler has to assume the worst, that you might get the most pessimistic pathological code upgrade at any point. But with local functions, everything goes because those can't be upgraded independently of the other local functions.
Yeah. So if you were to add an atom guard in a local function, it would get optimized away. So it wouldn't really be needed in the first place, but you could add it just to decorate and show that this is what's expected to come in there without any cost, if the type system can figure out that it's only atoms.
Mm-hmm. Yeah, I was thinking of something and then completely skipped me. Okay. Moving on again to the wider picture. Any particular favorites, any particular highlights on the work on the just-in-time compiler that you would like to highlight in this session? Like, what was the best part of this? What did you have the most fun with, perhaps?
Both times, I'd say reaching the prompt.
Yeah,
that's always amazing. Then you know that the worst is behind you. You can just implement a few more instructions, and then all tests will start passing in the next week or two. I mean, working your way to the prompt is a bit thankless because you have to implement hundreds of instructions by hand, and you're not actually seeing much progress. You're just working your way onto the next segfault, so to speak. So reaching the prompt, that's definitely the highlight for me. Do you have one?
Yeah, I mean, reaching the prompt is surprising how much code is needed in order to just get that prompt running. it's so much like NIF loading, and you need to get module loading, and you need to get all of the different things. It's like you're 80% there when you have the prompt there, and that's a nice. I kind of, for me, it was because I started like prototyping this and doing something very, very small, and just did a single module so that it was isolated into a single module, and just was implementing instructions on instructions, trying to get the different kind of modules working together, one working instructions in there in order to try the benchmarks that are part of the Hype benchmark suite, and then seeing that the performance actually was as good as I hoped, or even better than I hoped for those things in the early prototyping. That was kind of a big thing for me, because it's kind of like, yes, finally, this seems very promising, because I didn't think that it would be as performant as it was, which is why it's like was an idea that had been running around in my head for years before this, and I didn't think the performance would be what it was there. And then the second highlight was that when we got the entire Perf integration working, was huge. That's like, oh, nice. And finally, it became really useful there. I usually say that if I could have the Perf integration without the performance, I would still do the amount of work that we did to do this. There, the performance is just extra on top.
Mm-hmm. I remembered my question from earlier. So it's about, there was this one master thesis or whatever project about LLVM, which was integrating it as a backend of Hype, and it was getting a lot of performance by doing a type specialization for particular functions that it deemed necessary to specialize in this way. Would that make sense even in it's a very convoluted, I guess, question. Would it make sense to have this kind of, to try to specialize functions that the compiler does not have all the information about it, but it almost has all the information it needs to specialize for the general case? Is that a thing that you have thought of?
Yes, I know the project that you're talking about, and yes, I mean, I have thought about trying to do these things, but it's, I think maybe possibly the first step, because that kind of would be a more of a profile guided optimization. So I would say that you would run your system under some kind of benchmark, and then you would output type hints of some sort in a file for the different modules, and then run it through the compiler again that would optimize your code to say that this function almost have these inputs. But if it doesn't generate this slow code path or something like that, that would be my first step in such an approach, rather than doing something live, because doing something in runtime and these things, then you have problems with code loading and switching.
Yes, exactly. You cannot avoid. You need that. It makes no sense to do it without that. In a way.
And you need to be able to de-optimize and so on. So that would be the approach that I would do through something like that. And I believe the project that you're referring to, they did tracing. So they traced the functions,
exactly,
and collected the input, and then massaged that and brought it back into the Hype compiler in order to kind of optimize those parts.
Mm-hmm.
There. And they gained some pretty good performance from it, from what I remember.
Exactly. Okay, we are at our time limit. Thank you very much for being here today. There are 2 pending questions about performance regressions and what's the next big project that we will be celebrating in a few years. But I guess can take this in the Lucan. Thank you everyone for attending. Thank you, Lukas and John.